Friday's class tomorrow, February 12th. We are not meeting face-to-face. We're only meeting remotely, which for us means through this video. I will say I have your exams graded, and soon I'll have information for you. Soon, hopefully by sometime tomorrow, I'll have your grades posted. And I want to talk about some problems on the exam. There were a few that I guess could have been done better. And so I want us to understand that. And, some of those topics will be on the final exam, so take a chance to review them. But that'll come later. This is moving ahead in Chapter 3. As you remember, Chapter 3 is about techniques of integration. And by integration, we mean finding antiderivatives. Okay? So far, we know, antiderivatives, they're part of applying the fundamental theorem to the evaluation of a definite integral. And later on in this semester, we're going to learn some things about using antiderivatives outside of a definite integral. That is for the information we can get from the antiderivative itself. So we've covered a couple of sections. They were both represented on the exam. And so today we want to move ahead with the next technique in Chapter 3. And as you can see here, it's called trig substitution. Before we get into the details of this new technique, there is a certain trigonometric expression we're going to run into. And I want to talk about it before we get there. So when we get there, we'll know exactly what to do. Okay? And, maybe you learned how to do this in high school in your pre-calculus class. But certainly we haven't used it in calculus this year. And so even if you did learn it, maybe a quick review will be worth the time. So I'm talking about simplifying expressions of this form. That is a trig function composed with an inverse trig function. And each of these could be any one of the six. It could be the tangent of the inverse cosine, or the secant of the inverse sine, whatever. This trig function right here, any of the six, and this guy could be any of the six. And the key to understanding how this works is the way that we think about inverse trig functions. And if you were in my Calc 1 class, and almost all of you were, this is the way I refer to them all the time. Let me just give you a specific example. I'll pick on the tangent just randomly. The inverse tangent of x. Or, if you prefer, the arctangent equals the angle whose tangent is x. So I honestly believe that if you can just wrap your head around this, pretty much all of the mystery goes away about these inverse trig functions. Now, maybe you don't have any mystery with them. So great. You're in good shape. But for a lot of students, I know there is some mystery. And that's the key to think about it. It's every inverse trig function is equal to an angle. And what angle is it? It's the one whose, in this case, tangent, is that number. So, for example, the inverse tangent of the square root of 3 is pi over 3. It's the angle whose tangent is the square root of 3. So this is just restating a fact that we all knew. Maybe we all know. The tangent of pi over 3 is the square root of 3. You remember working that out, pi over 3 being an angle in a 30, 60, 90 triangle, or the angle in the interior angles in an equilateral triangle. And so it makes it easy to figure out the trig functions. And it turns out that for 60 degrees, pi over 3 radians, the tangent is square root 3. And we can summarize it. And notice, this trig function is equal to the angle whose tangent is the square root of 3. So I'll emphasize it again. Think of trig functions like this, and all the mystery goes away. All right, so that's not the expression I wanted to simplify, but it gets us started. And let me just illustrate with an example. This kind of expression up here. Any trig function composed with any inverse trig function. In that order, the inverse on the inside. So I'm just going to illustrate with an example. I'm going to take the sine of the inverse tangent of x. And I want to simplify it. It turns out that these expressions, a trig function composed with an inverse trig function, is not a trig function. In fact, it's an algebraic function. And what I'm doing now is showing you how to find that algebraic function. Okay, so here's how we do it. We look on the inside here. Well, I have the inverse tangent of x. That's an angle. It's the angle whose tangent is x. I can draw a picture of that angle. Well, thought I could. So here's a triangle. This is the right angle, and this is the angle. And I need to define the sides of this triangle so the tangent works out to be x. The easiest way to do that is to let the opposite side be x and the adjacent side be 1. Because tangent, is opposite over adjacent. So I could pick the sides to have any links whatsoever as long as when I divide opposite by adjacent I get x. So I'm always going to do it the simplest possible way. There's absolutely no reason. In other words, I could say, I'll do it in a different color. I could let this side be 2x, and then this side be 2, and then opposite over adjacent. That works out to be x. 2's cancel. But there's no good reason to do that. Just pick the simplest form. I'll do a little more complicated one in just a minute. Okay, and by Pythagorean's theorem, let me get rid of the gold or yellow so it doesn't confuse us. By Pythagorean's theorem, we can find an expression for the hypotenuse, and I need to do that because we need to talk about the sine, and the sine needs the opposite. The hypotenuse. So the Pythagorean theorem says the length of the hypotenuse of this triangle is the square root of 1 plus x squared. Okay, and then I remember sine is equal to, I'll write it over here like I did the tangent, opposite over hypotenuse. Therefore, the sine of the inverse tangent is x, the length of the opposite, divided by the hypotenuse, the square root of 1 plus x squared. And we did it. And notice, it's an algebraic function. It's not a trig function. So what we've shown here is this sort of weird function that maybe we've never ever thought about before. It's actually this function right here. And if it was what we needed to do, we could analyze that function and figure out lots of properties, the graph and so on, but that's not really our focus here. Our focus is simply on simplifying these kinds of expressions. I promised you I would do one more. Let me set it up. Okay, we want to simplify this expression, the sine of twice the inverse secant of x. That is the sine of twice the angle whose secant is x. Okay, in this example, I particularly want to emphasize the role that 2 plays here because it's crucial. It's non-trivial. You have to be careful. And we're going to see it later on. So makes this an important example. So remember, the inverse secant of x, that's the angle whose secant is x. And let's just remind ourselves, the secant is the reciprocal of cosine, so it's the hypotenuse divided by the adjacent. We'll use that a little bit later. Okay, and because of the 2 here, then I see that the angle is doubled. The angle whose secant is x, represented by that right there, is doubled. And then we send that angle off to the sine function. Well, when I say the word double, hopefully you immediately start to think of the double angle identity. And in the last section, we used the double angle identity for cosine. Here, we need it for sine because that's the function we've been given. So I'm sure you learned this. Maybe you know it. Well, I'll write it out for you here. The double angle identity for sine 2 theta, is 2 sine theta cosine theta. Okay, that's true for all theta. And that's different, of course, than the cosine one was. But it's going to help us find a simplified version for this function. Okay, so just like we did before, this circled in red is the inverse secant of x. I can draw a picture of that. And here's my angle. And remember, secant up here is hypotenuse over adjacent. I need that to be x. So I'm going to pick the hypotenuse to be x and the adjacent to be 1. So the ratio, hypotenuse over adjacent, is x, just like we need it to be. And then by Pythagorean's theorem, the other side of the triangle is x squared. The other leg is the square root of x squared minus 1. And therefore, this, the thing we've been given, we can simplify as using the identity twice the sine. Let me write that a different way. Twice the sine of this angle. Well, the sine of this angle over here is opposite square root x squared minus 1 over hypotenuse. So 2 times that times the cosine of this angle. Well, the cosine is 1 over x, adjacent over hypotenuse. And now we've done it. We found the algebraic function. Let's just clean it up a little bit. So I get twice the square root of x squared minus 1 divided by x squared. That is exactly the same function as the one we started with, the sine of twice the inverse secant. Okay, and we did it. The instructions were to simplify, and when you look at these 2 expressions, the original and the one that we came up with, we could maybe argue which one is simpler, but we can't really argue the second one. The one we came up with is really easier to understand. You can just see exactly how to calculate values for it, plugging in the x and squaring it and so on. Okay, so that's the trig review that we need. And now let's see what in the world this has to do with calculus, with integration. So I'll pause and set up a couple of things for us to think about. All right, as mentioned before, section 3 is about a technique called trig substitution. What we're going to do is take certain kind of integrals described below here, and convert them to trig integrals. That is, we're going to take functions whose antiderivatives we don't know, we haven't learned yet, make a substitution involving trig, evidently, and rewrite it, and we'll find that we get an integral that we could have seen in the last section. So we're going to reduce section 3 antiderivatives to section 2. And since presumably we have good knowledge of section 2, I just tested you over it, and actually those were some of the better done problems on the exam. So hopefully we're equipped for making the substitution to convert non-trig integrals whose antiderivatives we do not know, cannot get by the techniques we currently know. We're going to rewrite them so they become a section 2 kind of an integral, and then hopefully we can use what we learned there. Okay, so they all involve, we'll say, there's always some exceptions. Maybe we'll look at some later. But basically, we're looking at functions